All right. So let's start. Shiwali Mohan is going to be talking today on on modeling humans in collaborative AI systems. Shiwali received a BS in Instrumentation and Control Engineering at Delhi University and a PhD in CS at the University of Michigan, Ann Arbor. She's a senior research member, senior research staff member at Palo Alto Research Center, or PARC. For those of you who happen not to know, this is sort of like the Bell Labs of the West Coast. PARC's created Adobe, GUIs, mouse, object-oriented programming, etc. She studied how to design and evaluate human-aware AI systems. That is to say, systems that model and reason about uh, 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 their human collaborators. And with that, I'll give it away to Shiwali.
Okay. Thank you, Keith. I sort of put up my picture. That's me when we in the pre-COVID times. That's the last time I visited LA. I was super excited, so I just wanted to present this picture and say, like, that's how happy I look when I'm in LA, and I'm sorry that I wasn't able to visit in person. Okay, so let's just dive right in. Whenever I tell people back in India, my folks, my family, and I tell them that I work on AI systems, they all get super excited. And it's because like we have seen all of these movies in which AIs are doing all these awesome things. My brother is especially fond of Iron Man and Jarvis, and every time I tell him this is what I'm doing, he would say, hey, you're building Jarvis. And so if you just sort of think about how the general public thinks of AI systems, they think of intelligent collaborators, which are independent, long-living entities who have goal-driven and problem-solving behaviors. They interact and communicate with humans. They learn from their experience, right? So Jarvis helps Iron Man do awesome things, and it's very critical to Iron Man's success. However, if you look at AI research, and this wasn't true like in the early era of AI, but it's becoming more and true lately, is that the research has started focusing a lot on algorithms. So you would have a lot of data, and we're building bigger, we are trying to get more and more data, and we are just very excited about how much data we can consume in our models. So a lot of excitement about various algorithmic methods. Currently, deep learning networks, deep learning architectures are all the craze, and we are trying to see how big can we build these architectures, and and if these big architectures can consume all this data. So we pick our favorite algorithm, we show that it's better than state of the art, and we are sort of, the way we evaluate better than state of the art is like we have some task agnostic metric, right? So it could be accuracy for prediction tasks, it could be F1 scores if we are trying to do, again, prediction tasks. And then we sort of say, okay, we are done, like we're excited about having made all of this progress. And so the question sort of in my mind is that will algorithmic research by itself result in intelligent collaborators? And that's what people think of when they think of AI, right? So we'll just by developing these algorithms and putting them, and just doing analysis over their efficiency and accuracy, will be reached to intelligent collaborators. And the answer could be yes, right? So if we could eventually sort of fall upon these big networks that can do all kinds of intelligent behavior. But I'm a very impatient woman. Like I can't wait for that long. So what I sort of try to work towards is to have this engineering or systems view of AI. And here we have an AI system that's interacting with its world. It has algorithms that helps perceive the world. It has its own tasks and goals. It has algorithms that helps decide what next thing it should be doing, then algorithms that sort of help it act in the world and change the world, right? And the research behind designing AI systems is trying to understand how various different algorithms sort of fit together in a system that had interesting complex behavior. And USC is sort of no stranger to the systems view perspective. It's like Yolanda Gill's talk earlier this year that I went to and was super interesting, was about how do you build semantic workflow, which is AI as a system for helping scientists, right, do better science, right? So it's systems that matter, systems that excite me. And some of my training at University of Michigan with John Laird has been on how to design better AI systems that have multiple algorithms working together, what are their representations, what are the interfaces between algorithms and things like that. So it's super exciting. And the way we sort of try to build these systems is we have some understanding of the world model, right? We are thinking about how do we represent the state, what parts of the state are, what parts of the world are important to represent and are useful for reasoning. What is the action representation? What is the transition function? So if we had to apply an action to a state, what next state would result? How would we evaluate if we are doing good or bad? So and so there's a lot of discussion that goes into figuring out what is the right abstraction for this world so that this AI system can be effective. Right, but if you really think about it, the Jarvis and the Iron Man use case, right? So we're building Jarvis, we're trying to like really understand all the different things in the world. But what the question that sort of fits, what about the Iron Man, right? What about the human? The AI system is not just going about its world on its own. It's actually trying to do a task in support of some human goal that the person has, right? But if you really start looking at the science behind how do we model the human, how do we model the Iron Man, it's sort of missing. We don't know how to, don't have a good understanding of how to represent state actions or even formulate decisions. And this was highlighted in an AIJ article that came out in 2018 by Peter Stone, where they were going through all the different sort of modeling methods in AI, where the goal is to model another agent that's in your environment. And they realized, and they sort of, the conclusion they draw was that this research is sort of in its infancy and we don't really know how to model humans, so that AI systems can sort of reason and learn about their human collaborators. And in fact, AAAI presidential address in 2018 was also focused on the same problem, where Rao sort of gave this call to arms about human-aware AI systems, that AI systems must reason about humans. Because eventually, if you really think about the deployment, right, the humans are a critical part of the environment. They're not going away. So we are not designing AI systems to function by themselves. We are actually designing AI systems to help help humans of the system with their goals. So this is the central question that I usually want to add, that my research asks, is how do we model the human collaborator? And the models of the human collaborator have to be computational and explicit, because we have to then integrate them with AI algorithms. So they should be informative to AI algorithms. Just describing them qualitatively or in English is not, getting us there. We have to go to the computational parts of it. The second is that they have to be causal and prescriptive. So if you really think about AI algorithms, the way they function is, okay, I'm in state A, now I have these 3 different actions that I can do, these different states would result. So you need to have the model sort of define the state and the action space for you that the AI can then reason about and evaluate, right? And then these models must enable reasoning and learning about the human collaborator. So that's sort of like the desiderata for modeling, the kinds of modeling methods we want to use in human agent collaborative systems. So now this is a very big goal, and often like there are pitfalls when you're trying to build systems like that. And a lot of times as a young scientist, what I have felt is like you get very excited about the method, right? So, oh, this is the latest by LSTM, and I really need to learn about like the computations behind it, and I really need to understand the mathematics and the computation. And so if you get really focused on the method, you're sort of losing the big picture of at least what my research goal is to really design collaborative AI systems. So I've figured out these sort of 4 constraints that I use to then determine which kind of problem I want to study, how would I study, right? So the first constraint is that I define a problem where the AI success is dependent on modeling the human collaborator. So AI success is not independent of the human. Like we're not looking at, oh, can we just predict it with high accuracy, right? We're trying to sort of put the human modeling problem as the central problem in AI formulation. The second one, which is related to the first constraint approach, is developing human-centered desiderata. So we want to get away from accuracy and efficiency and all these computer-centric metrics, and actually focus on human-centered. What is it that humans want these AI systems to do, and design metrics so that we are making progress in the right direction. The third sort of constraint that I have is that I want to adopt methods from humanist sciences, psychology, behavioral economics, because these lines of study really have tried to understand human decision-making. thinking, right? So there's a lot of data there are a lot of models, there's a lot of knowledge out there. So I don't want to redesign this entire science, but actually understand how we can use the models that these scientists have figured out and put them in AI systems. How do we go from the descriptive models that human sciences would describe in the literature, and how do we get to more prescriptive and causal models? And the fourth constraint that I have on my sort of research approach is that I want to design interactive AI algorithms and embody them in a system. Because unless you put algorithms together, embody them in a system, like, you really can't understand if humans actually get the algorithm, right? It's if we're only studying the algorithm, we will only be able to study the computational parts of it. But if you have to study the collaborative parts of it, you have to put it in a system. So with these four things in mind, my remainder of the talk, I wish I could tell you, like, there's a modeling language for humans and this is how you would use it, but that's not the case. It's a hard problem. It's very convoluted. So the way I've structured my talk is that I'll go over three different collaborative AI problems, and I'll talk about how we model the human part of the equation and how do we put them in AI systems. And then the talk will end by some just higher level perspective on where this kind of research can go. So diving right in, the first sort of topic is interactive task learning, right? So what is the collaborative AI problem we are trying to solve in this research? So the sort of the use cases that we are going to deploy a lot of AI agents, right? There's Siri, Echo, in every home and every phone. Very soon we'll see a lot of robots getting out there. Walmart has committed to putting robots on their grocery stores. Amazon already has robots at their Walmarts, right? So there's intelligent agents, physical and non-physical, everywhere. Now it's hard for AI designers to predict all the use cases, all the tasks that these agents are supposed to do. And the question is that how would you scale, right? So one of the answers that the research community is exploring is that the AI method should allow the humans of the environment to program these AI systems to the tasks that they would like them to do, right? So right now, if you have to think of like Amazon Echo, right? So if you had to add another skill, then you'll have to hire a skill engineer who comes in and who programs it. This problem would become much more complex when there are robots out there, right? Because now someone has to like look at the vision parts, has to look at the task parts, and then program the entire robot, and it just doesn't scale. You cannot have a robot programmer for every robot deployed in every home or every grocery store. So how do we enable non-expert humans to program the robots or the AI agents that are in their environment? In 2017, there was this meeting where a lot of people from different parts of AI discipline, machine learning, cognitive architectures, robotics, psychology, NLP, we all met and then sort of said that, hey, interactive task learning is actually a field of focus that AI should have. And the goal of this research is to understand how to build robots and agents that can learn or teach humans through natural interaction, right? So not through programming, but natural interaction. And this is a sort of a strength that we want to exploit in designing our AI systems. Humans are natural teachers. Like the last time, recall the last time where you interacted with a child. And it's a lot of that caregiver-child interaction is focused on helping the child really learn different parts of its environment, right? So humans have certain natural tendencies to teach others. And a lot of human learning is driven by being embedded in social constructs. So how do we really exploit this naturalness of human teaching and then design agents that can then learn from human interactions? So to design such an agent, you have to shift, you have to get a shift in your perspective a little bit, right? So the classical machine learning is sort of, you have a data set, you have a model, and you're trying to fit the model on the data set. Interactive learning, like there's no difference between the data set and the model. It's very incremental, it's experience, and that gets compiled into knowledge. Classical machine learning is very phased. There's a training phase, there's a testing phase, and interactive learning. Like again, recall interactions with a child, right? It's very online. You're trying to set up different lessons for the child maybe, or you're trying to test the child, like, hey, can you pick up the red block, right? Things like that. And all of that happens online as the child is applying all of their learning to do something in the environment. And once the teacher observes the child doing something, they can then give it corrective feedback, provide encouragement and things like that. So there's no distinction between training and testing, and everything just has to happen together. Right? Classical machine learning is passive, so a AI engineer or a data science engineer will decide, okay, now is the training phase for the system, and now it's the testing phase, and now it's the deployment phase. Interactive learning, there's just no difference in these phasings. It's not passive, it's actually active, right? So when an interactive learning system figures out that it's failing, it actually has to go and get examples to improve its behavior, right? So it's all driven by where you're failing, where do you lack in knowledge. Classical machine learning, it's big data, so you want more and more data. Interactive learning, because here the constraint is that we want to learn from humans. There's a small data need right there. Like humans will not give thousands of examples of the same thing. They'll give a few salient, distinctive examples. And then the agent should be able to just use its reasoning capacity to figure out where exactly it needs. So it has to be very efficient with its data process. Classical machine learning sort of assumes that the data is confounding. You have to have all the right distributions. Interactive learning, you can assume that the teacher is benevolent. It's trying to actually teach you. So you could expect that the teacher sort of teaches you on simple things and then expects you to apply that knowledge to more complex tasks. So we want to exploit all of this sort of interesting learning structure that just falls out of when you are in an interactive environment. So at PARC, we are trying to study the embodied language learning problem from that kind of a perspective. So this is a part of the DARPA Gala program, which tries to answer, like, where does the meaning in language come from? And if you look at the traditional way NLP is derived, they say, well, the meaning is derived from statistical patterns of word usage. Now, this is very not useful for language and robots, right? Because robots are not just living in the informational world, they actually are living in the physical world. So they have to connect their senses and their actions to words. So the meaning is actually connected to what's being observed. There's a related branch that's now called grounded language processing. So imagine the visual question answering task here. The meaning is sort of derived from paired visual and linguistic stimuli. Again, it's like, again, the pattern recognition type task, right? Where you are trying to see, okay, if the red block is to the right of the green cylinder and you're saying yes or no. So you have to think about, how do humans use language? And there's this hypothesis from psycholinguistics literature that says that humans use language to refer to things in either the domain, in the environment, and in the common ground between different humans. So it's an attentional process, and that's the one that we are exploiting in this project. So imagine, like, if someone in the scene panel 1 here, someone said, move the green sphere onto the red cube. So now you have to use what you know about green and sphere to figure out, okay, this is the object that has to be moved, right? And this is the object, that the other object that I should be paying attention to. Now, the word onto sort of describes some spatial relationship between these two objects that I'm concerned about, right? And now this onto relationship does not even exist in this panel. You're supposed to establish it through some action, but you should have some understanding of what onto means, what kind of spatial relationship is being referred to. Right. And then the move action, you have to say, hey, these are the policies. So that if I pick up this object and then place it on this object, right, that's how I will achieve this action. So then you go ahead and execute it. So it's all of it is like driving attentions to different parts of your perceptions, different part of your domain knowledge about actions, different part of spatial concepts. So that's what language is trying to do. And we are trying to build systems that have linguistic comprehension that is sort of driven by how humans use language. So we are pursuing an advanced cognitive systems approach. So this is, again, an end-to-end system. We have a simulated robot that has a camera that's looking top down. You can see different objects. And the reason I'm saying it spans cognitive systems is it has flavors of very different kinds of algorithms, right? So we have computer vision algorithms that are built with deep learning methods. We then extract some qualitative relationships from that. Then we put those relationships through SOAR, which is a cognitive architecture that's designed to, that's inspired by human cognition. It can do higher order cognitive reasoning like analogical concept generalization. And finally, once it has decided an action, it then compiles back down the primitive actions into a control, like a continuous control space using inverse kinematics. So it's an end-to-end system. It's a hybrid AI system that requires, that sort of integrates a lot of different disciplines of AI together to produce complex behavior. So let me just very quickly show you. I don't have a lot of time to go into the details of how the system is built, but I just wanted to show you sort of how it functions. So here we have the robot, you have the camera, the simulated camera that's looking at the robot, that the robot is using the information from. Here you are going to see some interactions with the human. And here is like our online reasoner. So you'll notice that at none of the points in this learning, we take the system offline. Everything has to happen when the system is online in an interactive fashion, right? So the instructor then sort of can place an object in front of the agent and say, well, do you see a cone? So that's the verified task provided to the agent. And now because the agent doesn't have any information about any concepts, it just indicates a failure, it's like doesn't know. Right now, because the instructor has seen the agent doesn't know the cone concept, you can try to teach it, right? So now the instructor will place and say, well, that's a great cone. The agent will use all of this information to then start learning the concept around the word green, around the word cone. So it slowly like sort of learns this joint models of perception and language, and it's all compositional, it's derived in relational representations. It has all sort of the nice properties you would expect from an interactive learning system. Okay, I don't know why this stopped. Right, so now you can give it another example. You can say, oh, that one is a blue cone. And what you'll see now is that it sort of can tell that, well, I already know the cone concept. I already had some examples from it. Now the new concept being told is blue. So it's very attentional, right? It explicitly reasons about its failures and its learning. So you'll see it in a moment that it knows which concept to learn and how to sort of start storing examples in that concept. Just giving a pause. I don't know why this is a little slow, but again, like earlier, there were 2 new words introduced to it. So it knew I'm trying to learn 2 different concepts. Now you're trying to use a previous concept, right? So it will generalize the cone concept by storing more examples on it, but it also knows that a new concept has been introduced, right? The blue concept. And so slowly it sort of accumulates these examples, and then you can teach it spatial relationships by showing things like, well, the red cylinder is to the right of the green cone. So you sort of build upon the knowledge, right? You start with the simplest lessons first, you give it different examples of objects, then you start building and accumulating knowledge up, and it's compositional in its learning, it's compositional in its language processing. So it has a lot of very nice properties. And the other sort of interesting thing about it is that you can eventually build it up to action, right? So let me just try to get to the parts. I'm sorry that I can't play this video in its entirety, but I'm happy to do it in my personal meetings. I'm very excited about it. But basically what you're trying to do is you're trying to build these representations that are all not only useful in recognizing an action happening, but also for action planning. So there's no separate like action planning system or action recognition system, the vision system. It's all integrated together because you are trying to learn the right central representations for recognition and action and planning and things like that. So going back to so our paper is going to be presented at the conference Advances in Cognitive Systems in August. And so it talks a lot about that, gives the details about how the system is built and how we're thinking about evaluating it. So I'll encourage you to go read it and have some references in my talk, and I can send those references out too. But what's sort of exciting about it is that we proposed a new evaluation framework or new evaluation scheme for evaluating interactive agents, right? It's not just accuracy that matters, because the agent will at one point start learning accuracy, but it also matters how it's learning, how quickly it reaches to accuracy. So we are thinking about what all different kinds of things can the agent learn. We've shown that it can learn visual, spatial, and action concepts. It actually can plan with those representations, and which is sort of a first in the literature. Like usually people think of only recognition as one thing, action as another thing, but bringing it all together into an end-to-end system is sort of something that we are very excited about. We are interested in if the learning is active, if the agent is actually trying to get examples that are the right examples for given its learning method. We are interested in the quickness of learning, because humans can only provide few examples. So how quickly does the agent learn? How general that knowledge is? How can it use its reasoning mechanisms to quickly generalize it? Right. So not going into a lot of detail, but I wanted to point out that this new evaluation scheme is critical. If we want to push for interactive task learning agents, we have to figure out how exactly are we going to evaluate them, and that evaluation has to look different from just the typical metrics of accuracy, because we're thinking about humans and how humans teach. So taking a step back, I just had presented those 4 constraints that, how I sort of think about my research agenda. So I just wanted to demonstrate how the interactive task learning problem actually fits those constraints, right? So we defined a human model-based AI problem. We said, hey, humans have to teach AI. So we are taking these humans really seriously, and we want to model how humans teachers teach, right? The second thing is we define human-centered metrics. So here we are saying that it's the quickness of learning that matters, active learning that matters. And we are not sort of really focused on the F1 scores, but we are trying to see the learning curves and the shape of them to then see how good the agent's learning is. We adopt a lot of math methods from cognitive psychology and psycholinguistics, who give us with a lot of sort of knowledge about how humans actually approach language. What does language understanding mean for humans? And the fourth one is that it's a hybrid AI system. It's end-to-end. It has behavior that you can observe, you can evaluate with humans. It incorporates all the nice things of deep learning, cognitive architectures, and all of that. So I hope like this is sort of, you see an example of moving away from algorithms and you putting them together in integrated systems that have complex end-to-end behavior. And that's how I think we will make like reasonable progress towards building Jarvis, right? Is actually trying to figure out how do you put these algorithms together? What are the interfaces? What are the representations? And all the related questions like that. So as we develop this, we have quite a few publications, all published at central AI venues. We are trying to go to more robotics and HRI venues. Those people are sympathetic to the research. I wanted to point out to encourage you to all go and look at Michigan's Rosie robot. So that's what my advisor, John Laird, sort of is leading, that research project. And the robot has learned, it can learn over 60 games and several like robotics manipulation, navigational tasks from natural interaction. Right? So that's super impressive. It's like humans can actually come in and try to teach the robot. And now, as I understand, the research focusing on more on the naturalness of teaching, but it's very exciting that we can think about sort of these interactive agents that are learning from natural interaction. So changing the pace a little bit, the second problem I wanted to talk about was the sustainable transportation problem. And I think living in LA, it's not a problem now, but when I visited LA, this was actually a pretty big problem, right? So energy consumption in transportation is tremendous. Right? It's one of the biggest consumers of energy. 29% of energy in the US was spent on transportation. Far from efficient, right? There's some parts of the network, the transportation networks are underutilized, others are overutilized. There's a lot of congestion, and congestion alone wastes 6.1 billion hours and 3 billion gallons of fuel, right? So it's a very wasteful system. So the government, and other policy organizations are very interested in understanding how can we resolve this? How can we make this a little better? So it's become a technology and a policy problem. ARPA-E's Transnet program that ran from 2013 to 2018 was based on this premise that there are ways in which we can, improve this transportation system. And the idea was that there's new modes of transports that are available now, right? You have Uber, Lyft, like all these ride-sharing applications. You have e-bikes that now anyone can rent from different spots. You have trains, you have subways, you have buses, you have bikes. Some people might want to walk and run. So there's this bigger multimodal transportation sort of planning that you can do to figure out what is the most energy efficient way to transit between different cities. And then the idea is that if you have the energy efficiency as your objective outcome, then you can try to make cities more objective, more energy efficient. There's one problem in this though, that if you could come up with the best plan, the most energy efficient plan, it will not be successful until the humans of the transportation system actually adopt that plan for their own transit, right? The humans are the key decision makers of this problem, and you actually have to influence them. So our JR paper that came out last November tries to study this problem. It's trying to study the influence problem for transportation so that our cities are becoming energy efficient, right? So imagine we have a person, just Dr. Jane. She has a transportation assistant installed on her phone. She goes to her work every day. She goes at night. She sort of the agent knows that she leaves for work at around 9 a.m. or she has to be at work at 9 a.m. The agent has access to her transportation network, so you know that she can walk, she can bike, she's excited about all these things, right? So now the agent sort of has to figure out the right time to sort of send her a message, right? And give her an acceptable option, right? Instead of driving, maybe you can walk to the bus stop and there's a direct bus to office. And the agent sort of makes this recommendation based on that Dr. Jane cares about her environment. She values free time during travel, right? So if you put her on a bus, then she would have some free time that she could sort of use to wind down, read a book, and things like that. And then you want to frame that message in a compelling way that actually appeals to Dr. Jane, right? So maybe our Dr. Jane is very green conscious. So you say that you're contributing to reducing emissions by 10%, right? If our Dr. Jane cared about monetary incentives, you could say that, taking a bus is this percent cheaper, right? So you have to really understand the person if you have to influence their decision making. And that's what we wanted to study in this research project. So to then try to understand, so we focused on this acceptable planning part, right? How do we figure out which multimodal transportation route is actually acceptable to Dr. Jane, given her current, given her current transportation network and something that we know about her. So to model this, we went to the choice theory from behavioral economics, and this was a foundational paper that was written by Tversky and Kahneman in 1986, in which they studied how do people even make decisions, what kinds of mathematics underlies their decision making. And they said that the decision making or the choice of different modes of transport is based on the utility that's associated with each mode, right? So there's a person, there's a mode of transport, and it has some utility. The utility has the mode dependent component, so you would have the cost of taking that mode of transport, that how long you're taking it for, how far you're going, how much time, but it also has a person dependent component, right? So the income matters, education matters. So together it's a linear combination of some things about the mode and some things about the person. And what you observe as a choice is a ratio of, it's proportional to the portion of utility, right? So if the probability that someone will take, person P will take mode I is dependent on how much value it has as compared to the total value of all possible options. So in the paper, we sort of said that, hey, if we are trying to get someone to move from driving to go, at least say maybe biking, we are trying to ask them to pay a cost, right, which is represented by the change in utility that they will face from driving, going from driving to walking, right? So what is this cost? And then we show that, well, that can be represented as a probability of a person taking a recommended mode of transport divided by the probability of the person P taking the usual mode of transport, right? So if we are recommending walking, then this would be the probability that someone would walk divided by the probability that they would just take a bike. So we are trying to, in order to influence them, we are trying to get them to pay a cost. Now the question is, are they willing to pay a cost? So the plan, so the systemic approach to this was that we have to recommend a plan that's acceptable to an individual given their local transportation context, right? So we formulated a multimodal planning problem. It's typical, how would you would do path planning where you have different nodes representing different sort of intersections, and there's you have edges between those nodes that represent different ways those intersections are connected. If you are trying to only do driving only path planning, then the edges are just roads. But if you're trying to take it multimodal, then you have multiple edges going between these nodes, and there's a planning formulation that we sort of proposed in this work. What I'm going to focus a little bit on is the acceptability part of it, the human-centered part of it, right? So there are two questions that are critical. The first one is, how do we estimate this acceptability? We defined it, but we have to, if in order to build a system, we have to sort of estimate it for every individual user, right? So for Dr. Jane, what is the acceptability if we of walking if we just recommend it to her? And the second one is, like, even if you build this system that is multimodal and it's providing acceptable plans to humans, how do we measure the impact? Like, how do we even know that we are making the city transportation more sustainable? And both of these are like big challenges. I'm very excited that we made some small inroads in trying to understand how to measure acceptability and how to sort of evaluate the impact, right? So the paper describes the how we can estimate acceptability, and we apply a machine learning approach from it. And the reason for applying machine learning at this point is that the way we define acceptability, it sort of said that it's a ratio of probabilities, right? Now the machine learning methods, if you formulate a multi-class prediction problem, so given a trip and certain properties about it, if you can predict, if you can sort of label if you can predict the mode that someone is going to take, the machine learning models also have a byproduct that they also will give you a probability distribution of all these different modes. So we can use these probability distributions to then figure out the sort of switching cost. And once you have the switching cost, you can then try to sort of find the route that has the least switching cost for Dr. Jane, given some things that we know about her trip and about her personality, and then we just sort of try to experiment in that way. So we found this very cool data set from Caltrans. It's called California Household Travel Data Set, in which they measured a lot of different people and different kinds of trip people make and what modes of transport they take from these when they're making these trips. It has a lot of features that are interesting. So we have trip-related features, we have person-related features like demographics and education, the transportation network, so they recorded people if they have transit pass, if they live close to a bus line, and then also experience, like whether they have records of how many bike trips that you take in the past, right? So we can sort of develop a predictive model that from this data set, and then we use that, the probabilities from the predictive model to then measure acceptability. So now we have sort of, we have defined acceptability of a plan. We have figured out a way to estimate it. Now the question is, like, does it really matter if we use these methods and we try to influence someone's decision? Will they actually change their decision? And that, I think, is critical, right? And if it just could be that these things are nonsense and no one really cares about all of this mathematics and are really highly accurate machine learning models, because the sort of recommendations that these models are generating are not exciting or not useful to the person who's supposed to be changing their behavior. So to sort of study that a little bit more, we actually ran an acceptability study. So we adopted methods from behavioral economics and decision theory, and we sort of designed a set of surveys that tried to get at the influence problem. So we designed a set of experiments. These are called choice experiments. So we selected 49 people. These are people who are regular drivers in LA, and we asked them to give us like 3 or 4 different regular trips they make in a week, right? So we asked them, like, consider the past week and think about what kinds of trips have you made. So we had a record of those trips. And then in the next set of studies, we said, we gave them the original trip. We said that, hey, you usually take this trip. And what about this alternative? Like, instead of driving, would you want to take this alternative? Like, is this alternative interesting to you? Right. So the alternative, it was computed based on our machine learning models. And then we said, it had some qualitative components to it. So it just described the sort of the time that you would leave. But it also grounded it out into a map. So it said that this is, the route you would be taking. And is this, and then we asked them if this is actually useful, like if we provided this to you, would you take it? Like, are you likely to use this recommendation? And then our data, it's very preliminary, right? So it's still very scenario driven, a simulation. Like people are not making actual choice. They're just like trying to simulate that choice. But there is indication that if you computed the acceptability as we define it, and you estimated it with the machine learning models, you actually can influence adoption, right? So there was some useful signal in all of that math that we just did. So then to actually say that, if we adopted this kind of transportation planning scheme where everyone is being given, is being recommended these different energy sustainable modes of transport, what would happen to the city at the large scale? So then to measure the impact, we adopted methods from complexity science, transportation modeling, and agent-based modeling, where we actually simulated the entire transportation, LA's transportation network. It has 170,000 roadway lengths and over 1 million daily transit trips. And then we so this is also done by our collaborators. So we had a state-of-the-art simulation model of the LA region. So it actually simulated people driving across LA. And our experimentation was that let's try to influence 10% of the population, and let's use the model, the adoption model that we built here, to then determine their behavior, right? So if 10% people were sent a message, there's some likelihood that they would actually adopt it, right? And we studied that model from in our study here. And so the conclusion was that if all of these things aligned together, we could look at 4% energy savings and 20% time savings in Los Angeles. So so just wanted to talk a little bit about the context, right? We want to use here, we're trying to use the AI systems, the human modeling, all of that together to help inform certain policies, right? So the policymakers, the transportation designers, they need to understand if they have implemented these policies, if they're trying to incentivize certain kinds of schemes, what would happen to the system, right? And these kinds of models are extremely hard to build, and agent-based modeling is one way of doing it. And so a lot of our the research that we report on is figured out on how do you model the individual agents that are moving about in this simulation system. So taking a step back and just going back to the four sort of constraints that I had, again, this is because we're trying to influence people. It's a human-centered problem. We adopted acceptability and adoptions as metrics, as opposed to just looking at the efficiency of energy or just the efficiency of computation. We adopted methods from behavioral economics, complexity science, and we designed full end-to-end AI systems that has multimodal planning components, machine learning components, and we didn't really explore the embodiment as much, but then we expect an embodiment in an application, right? So I talk about that a little bit. Okay, so again, some papers, a lot of them, some of them are at AAAI, but I was excited to present this work at the conference on AI ethics in society. So that conference really cares on like what is the impact of using AI methods on society. So I was excited to present it there. We also tried to connect it to sort of get to audience at intelligent user interfaces, because it sort of lays the it sort of explores the sort of computational principles that underlie intelligent user interfaces. So we got some traction with that community too. So moving on to my third problem, which is the health behavior change problem. Like the problem is that the healthcare cost because of unhealthy behaviors is tremendous, right? So National Institute of Health is really focused on how do you reduce this cost? How do you reduce the cost to the healthcare system caused by people having unhealthy behaviors? And one of the most impactful ways of reducing healthcare costs is to provide get people to build healthier behaviors is human-to-human, individual, personalized coaching, right? So you have a lifestyle coach who looks at what kinds of things you eat, how much exercise you're doing, how much activity can you squeeze in a day, and they help you figure out like what your right goal should be, what right activity goal should be. Should you be eating more vegetables? And they help you track your progress on those behaviors, and eventually like people do shift to healthier behaviors and sort of see reductions in diseases that come with sedentary behaviors. The question is like, if everyone could get a personal coach, it would be awesome, but it's too expensive to actually get a personal coach. But we know that computation devices are extremely common. So the question is, can we use these computational devices, intelligent systems to support health behavior change? And this is like so our paper paper that appeared early this year in the Transactions of Interactive Intelligent Systems is sort of studying one such problem, like how do you help people and sort of encourage them to walk more. So here we have trainees. So we are designing intelligent coach for trainees are people who are managing diabetes. The embodiment is in a smartphone application. Through human agent interaction, we assess people, how much are they walking every day. We have people report on their walking behaviors. We have weekly goal setting interactions. And then underneath all of it, underneath all of this behavior is our AI, it's our adaptive goal setting, scheduling and planning algorithm that takes information from people and then adapts a plan for them and then sort of keeps them on the right path, right? So the paper contains a proposal for a model that underlies the goal chain, the adaptive goal setting. And this model is inspired by the sort of how physical therapists use of the kind of information or the kinds of frameworks that physical therapists use when they're trying to help people to exercise a little bit more. So usually, so just a brief overview of what the model does is that our goal is to get people to walking at the recommended level of activity, which is 30 minutes of moderate walking 5 times a week, right? So it's somewhere over here. So this is how much you're supposed to walk. But oftentimes sedentary people are maybe walking over here, like somewhere right down here. Now, if you start recommending them to walk at this level, they will fail very quickly, right? Because their strength is not built up enough. They will get tired. It's too much, right? So then they start failing and they will just never get to their goal, right? So the goal of this, the AI that we built was to actually put them on this ramp, which has small steps. So every week you increase your volume of exercise. That's the amount of exercise that you're doing a little bit. And then you walk up this ramp and then you will eventually get to the goal. The problem usually is that what should be the height of these steps should be. And that is what we personalize based on the feedback that we are getting from people. So we either would make, the staircase a little bit harder to climb if someone is very, has a lot of strength and they're ramping up very quickly. We adapt the algorithm so that it puts them on a sharper slope. Otherwise, you sort of reduce the slope a little bit, and then slowly through this adaptation, you find the right slope for them, and you are just personalizing this growth capability model to the specific thing that a person really needs. And the hypothesis was that if you could just personalize the schedule of exercises based on this model, then people would stick around it longer, and then they would actually build up good behaviors. So the sort of we built this model, and then the way to evaluate this kind of technologies is sort of, we came up with this interesting four-pronged multidisciplinary approach to actually understand the efficacy of systems like that, right? The first question that we asked was, is the AI system actually adaptive? So here we started doing what typical AI systems people would do, like we're trying to simulate how it's reacting to different kinds of trainees. So some trainee has no exercise background and they have moderate growth in their capabilities. So what would the agent do for them versus a trainee B, who starts with no exercise but has a low growth potential. So what would the agent do for them? Those are the green bars, and the trainee C has light exercise and a low growth model, right? So we are trying to characterize, like, does the exercise recommendation differ based on different trainees? And the answer was yes. So we got encouraged. The second thing then we did to evaluate the system was that we went to experts, like these are physical therapists who do this on a daily basis, and we gave them case studies for different patient profiles that we built up for this domain. And we said that, and that case study was designed as, like, we would describe to them the case, and then we would say, hey, expert A said, or like a recommender A said this goal, the recommender B said this goal, the recommender C said this goal, and we just hid the AI's recommendation as part of this set of recommendations. And we asked the expert, like, which one of these recommendations do you agree with? And then we showed that the way we had built a system, our system had the most sort of agreement with the experts and how experts sort of processed this kind of sort of case studies. The third question that we wanted to ask was, because it's an interactive HCI system, we wanted to ask, like, the trainees, our target population, can they actually use this app and the interactions with this app to present the right set of information for the AI to sort of optimize over, right? So if the AI doesn't get good information, the AI is useless. So you have to actually study the interaction parts independent of the AI and just say that, are those interaction measurements useful? So we did some qualitative studies with participants managing diabetes and depression, and we report some scores on the usability of the app and the acceptability. And then once we sort of figured out that the AI is sort of right, the HCI parts are sort of right, we then went to a deployment of this app to people. And I was very excited about this because this was 21 participants managing diabetes. They used our app for 6 weeks. And in ecological context, right, they're using this app as they're living their lives. So this is so different from how typical psychology studies and how different, HCI studies are done. Like, you're not trying to bring these people into the labs. We're actually sending some of our AI methods out into the world and then having people interact them and then evaluate AI that way. And in the paper, we discussed that, the participants who were using this app, they showed increased exercise volume. There were some problems. People were optimistic with self-assessment. So the AI algorithm started at a very tough space because people just thought they could do much more, but they weren't able to do it. So then the AI, but because the AI was adaptive, it was still able to recover from those kinds of measurement errors. We showed that setting personalized goals matters. We sort of showed that the way we are measuring people and their effort they're putting in actually matters. So this was super exciting. I've never done studies like this. I had never done studies like this before. Usually as an AI systems person, a robotics person, you sort of see how people interact with AI systems for small periods of time. So this was sort of mind-blowing. So I'm very excited about this one. Again, just going back to my metrics of how to focus research on the right direction. This is, again, a human-based, model-based AI problem. Unless you really model the training, unless you really understand what underlies their behavior, you can't really coach them properly. We focused on human-centered metrics. So we worked with experts to figure out what is it an expert physical therapist really cares about when they're recommending exercise. And all physical therapists said, the safety is the first thing. I would never recommend someone an exercise that I think they would harm them, right? So we really optimize our AI design to use safety as the first metric to optimize for. We adopt methods from humanist sciences. We have cognitive psychology, some guidance from physical therapy. We adopted HCI methods. And then again, we designed these end-to-end AI systems that have, this measuring behavior, adaptive goal setting. We embodied it in an app and we evaluated it that way. So that brings me to the end of the technical parts. And I just wanted to sort of go back to my higher level view and talk about human-centered AI just at a higher level. Right, so as AI scientists, we're sort of trained to think about this. We're like, oh, we are trying to design an intelligent system. It's operating in an environment. Let me really try to understand the environment and let me build all these really cool AI systems. And that's where we sort of end at. The problem is that deployment scenario is not the right deployment scenario. There's always going to be a human involved, at least one human involved, right? Because we're not designing AI to just live in its world by itself. We are designing AI so that the humans' lives are improved or better or facilitated somehow, right? Even for driverless cars, you just can't assume that the driverless car is autonomous car is just going to move about by itself. You have to care about the driver. You have to care about what they think is dangerous. Do they trust the autonomous car? And so humans are not going anywhere. So we have to put humans, the modeling of humans, at the center of AI system design. And that's the only way we will ever get to adoption of AI systems. Otherwise, if we just design sort of AI systems independent of the human, it's not even clear if the humans would adopt them. Right. So I talked about interactive task learning, and I said that, what if we had designed intelligent systems in a way that was not really useful for the human of the system, right? So then we talked about we are trying to do some work on how can the human of the system actually improve the intelligent system's behavior based on their own goals. The second problem was focused on if the intelligent system is trying to influence the human's decisions in the environment, right? So then you have to model what goes into human decision making, and then the intelligent system is designed, optimized to sort of influence that decision making. That was the sustainable transportation problem. An even more complex problem is like how through several different, how would you influence human behavior so that you actually build up a habit, right? So that was our healthcare behavior change problem. And there are some other problems where you sort of, I didn't get to go into, but there are like, what if the intelligence system is collaborating with the human? So the intelligence system could have different objective outcomes, like this is the gaming scenario, this is the more collaborative scenario. So regardless of whatever the scenario is, you have a need to model the human, and we really need to understand how the human is interacting with the system. And it's easy to sort of think that this is a sort of, as AI scientists, we will just design this part, and then this is left for the psychologists or the HCI folks to study. But it's like that can't, that will not scale. Like we have to sort of make this an AI problem, really understand what are the different ways humans interact with intelligent systems, what are different roles humans and intelligent systems play in collaboration and influence and learning, and then understand how we can design intelligent systems from that way. Just nearing the end of my talk. A lot of colleagues have collaborated on this. I'm really thankful for all these friendly people who have worked with me, who have talked to me about these ideas, these crazy ideas. Very thankful for all the funders. My work has been funded by a lot of different kinds of entities, so really grateful that they had all these cool problems that I could sort of study. And this is sort of my final slide. I'm going to end it here. And I just wanted to sort of just circle back to the overall sort of goal that motivates me, that drives my research, right? That I find it a little distressing sometimes that AI and ML sort of is considered, it's just computer vision or NLP or games. And anytime you try to do, for example, I tried to talk about sustainable transportation as an AI problem, and then there was this concern about, this is not an AI problem. It's actually not true. Like this, somehow as a field, we have been trained to think that these problems are AI problems and other problems are not. But they are. And these are actually truly hard and extremely interesting problems that are outside of these traditional domains. And that's where we have to look at, like as we're trying to study how intelligent systems change human societies, we have to go out there and find all these interesting problems. We have to look at, sustainable transportation and how can we help? How can AI scientists help there? Look at healthcare, how can AI scientists help there? And just really understand, really exploit the potential that AI has. And it's not even just the question about deployment, it's also the question of like really pushing the frontiers of AI research. If we keep on focusing on these problems from these specific domains, we are not even studying the full frontier, right? So we have to, and that's what drives a lot of my research. We have to look beyond prediction into long-term sequential decision making. The second point that I sort of wanted to make was that humans of AI are important, right? And even critical. You can't just design systems with humans as an afterthought, and that way we will not do the right thing for the human. We are not really studying the right problem. So making them central to intelligent system design is what would help us sort of develop a comprehensive understanding of human AI ecosystems and then really improve adoption of AI in human societies. So that's my contact information over there. I'm very happy to chat with you, to talk to you, to email you. Just please feel free to ping me at all of these things. And I will end my talk now and just keep the slide up in case people have questions for me that they would like to email to me about. Thank you.
All right, thank you, Shiwali. I guess we'll just have time for one question. And
Okay.
there is a question from Manali Mohan,
Oh,
which their question was related to the interactive learning you described. You
yes.
compared the you compared. I'm sorry, there might be a misspelling here. You compared that to how a child learns. How does the agent at some point even want to learn new things or tasks without instigation? Like child would if they feel the need, especially as they become more and more exploratory. This is in the chat window.
Okay.
You're free to see this question too. Would
Oh,
you
okay. I actually don't know how to access the chat window, but I'll try to. I guess the question was, how does the child recognize when they're failing?
let me better understand. How? Yeah, I guess how does the agent how does the
I
agent
guess I could.
understand what
Yeah,
it
I'll
needs
just.
to know? Yeah.
Yeah. what it knows and doesn't know. So that's actually driven by, it's a very good question, and it falls out of the instructor learner interaction, right? So if you really think about it, like if the way parents interact with their children, they would test the child. They would try to test the child. They would say, hey, can you pick up the red block? Can you know, I meant the red block, right? They have these probing interactions. And the reason for those probing interactions is that exposes something from the child's learning, right? So a child is trying to learn how to pick up the red block by continuously asking the child to do it. And if the child fails, right? So maybe the child picks up the green block, then the parent can build a model of the child and say like, okay, maybe it doesn't understand, you know, the color distinction. So you would try to give it more examples of that. So this sort of testing, then training, then revising the training, this kind of interactive sort of behavior just falls out of a learner and a trainer sort of interacting with each other on a learning task. So that's what we're hoping to exploit when we're designing AI systems.
All right. It seems we're out of time, but thank you again, Shiwali. And it seems that
Thank you,
Daniel
Keith.
Schwab has a great question. Daniel,
Okay.
I hope you'll be able to talk to Mohan one-on-one. If not, I will incorporate this question into my one-on-one talks with her. With that,
I'm happy to stick around and answer questions during the break as well. So if I don't know if there are a lot of questions, but I'm happy to.
Okay, in that case, yeah. How about if people want to leave, they're free to leave. And if anyone wants to stick around, they're free to ask questions. Um, and with that, let me ask you a question that Daniel Schwab asked, which was,
Okay.
how can we incorporate human values into such models?
Um, I haven't really thought that through. So I'll be frank, because I'm so focused on building these systems that have a specific problem that we're trying to solve, I haven't really thought through the value, the morality of the system side. But in the transportation behavior things, we were trying to study what would make a message compelling. So I didn't talk about this research, but we have a workshop paper that talks about, and our journal paper actually describes some parts of the human value system. So we studied uh, there's a scale called the susceptibility scale, susceptibility to persuasion scale. And there are different ways where you measure different people are susceptible to different kinds of influence, right? Some people listen to authority. Some other people may listen to, the objective outcome. Like, so the authority, you want to formulate the message that you're sending to people based on what kind of influence they're most reactive to. So someone who really believes in authority, you want to frame the message as like saying, oh, Al Gore says, or Obama says, if you took a walk today, you'll save the planet or something. And that's how we at least think they would react to. Some other people who are much more about the objective outcome, right? They might think, okay, I took a bus today. How much energy did I actually save? Some other people are more motivated by their social circle, right? So that's so in that case, you want to say that, hey, your neighborhood is trying to, reduce the energy consumption. All these different people in their neighborhood walk to their offices today. How about you walk to it, contribute to that sort of social goal? So that's how we were thinking about, at least in that specific problem, how would we try to bring some of the human values into the influence system. But I sort of agree, for the interactive task learning and the health behavior change, we haven't really explored those parts, and we have focused on the specific task metrics that we cared about. But thank you, it's a great question, and I think a sort of a very interesting direction to take with this research.
That's great. By the way, I gotta leave in a second, but there's just one
Okay.
more question. Which was they say they have a question regarding potential risks and ethical concerns about having these systems influence how we learn. Do you have thoughts on these systems being used to manipulate humans towards certain activities or values? I think this would be alike to social bots, if you know what those are.
I don't know what social bots are, but I totally understand the concern. And I think in the current climate, the AI technology climate, that is something that we have to be really careful about. And I think, as a scientist, I do think about the impact and of the kinds of systems we are building. And so the first thing I think as an AI scientist, it's our responsibility to think about the social good goals, right? So Milind Tambe from USC, and you all I hope have interacted with him. He sort of started this. He's at the leadership of this movement of AI for social good, where the goal, the explicit decided goal is to build systems that are trying to do some social good. And you are formulating those problems in that way. So sustainable transportation, for example, could be a social good goal. So starting from there, I think it's critical, right? If you are just trying to build solutions for games, you will never really achieve the social good goal. So saying that that's what the goal is matters. So as a scientist, I try to pick goals that are more humanist. They put the goals of human society at center. The other then concerns start coming in through methods, right? So the sustainable transportation method that I recommend, that I sort of recommend, that has this risk that it would if it were to be deployed, it would try to get people with lower income to take more buses versus, so basically they would have to pay a bigger and bigger cost to then reduce the total energy expenditure that everyone benefits from. So that model for sure has this risk of trying to offload some of the burden of sustainable transport to someone who comes from a poor neighborhood, right? Because it's using the neighborhood characteristics to make a determination of if someone would adopt it or not. So in that case, we then have to really look at the features that we are putting into our model and really understand the impact and really think it through. Unfortunately for this research, we weren't able to sort of understand that problem well, but I would say that that's definitely a risk and we should be doing better there. The health behavior change, the way it's constructed, because it's sort of built in while interacting with physical therapists and sort of trying to follow their principles, I would think the risk there is much less because it's much more explicit, much more details driven, and it's actually going into the core of aerobic physical capability for aerobic exercise, and that's what it's trying to model. So as long as that understanding is general over all kinds of populations, I would think it would not really vary, but we wouldn't know unless we actually test it out with people. But the risk is much lower. But the sustainable transportation one, I worry about those kinds of models. So thank you for bringing it up. I think that's where, as AI scientists, as we are trying to develop systems for different problems, we have to be really careful about what kinds of problems we are solving. I personally don't get very excited about hey, face recognition, and now we put up the face in this way, and then can we recognize this more, and now let's do adversarial ML, and now let's try to generate a lot of different faces. Where is it going? What are we trying to achieve? So as AI scientists, I think we have to really think about what kind of problems actually matter and pick up those problems as AI problems and really try to build solutions for those, because I really worry that if we don't do that, then problems of real impact will just fall on the back burner and we would be stuck doing games, which I don't even know if some of the learnings from there scale to real problems.
I see. All right. Thank you so much for your talk. I think we'll have to close this out now. But I look forward to talking to you later today, as will many other people who will have one-on-one talks with you.
Okay, thank you, Keith. Thank you for hosting. I'll just stick around just in case there are other people. I would have loved to come down there and chat it with you all, but
Okay,
unfortunately,
for sure.
this is the best. Yeah.
For sure. And at the bottom of your screen, there should be a little button for chat, so you can see when people send messages to you.
Okay.
I'll stop recording now, and I will head out. All right, so have a good day.